What I want to talk to you today is the idea about using catalyst-controlled CH functionalization, especially directed towards very unactivated CH bonds. So first of all, let me introduce you the people who are involved in this project. So the main player is Quangbao Liao. He's a third-year graduate student in the group. But several people have contributed in different ways to where we are at this stage. So Jorn Hansen, who's now an associate professor at Tromsø University, was the one who had the idea behind the catalyst that is driving this program, and introduced you to the structure of those catalysts in a little while. Cha-Ming Chuen was involved in characterizing those catalysts and determining the full scope of them. David Gupta was involved in developing the reagents to make them more robust, to allow them to do this type of chemistry. Solomon Negretti was involved in a key structural element that became part of these final catalysts that I will talk to you about. Hannah Ferguson-Johns, an undergrad in the lab, also was involved in developing some catalysts. And you'll see the structural elements of these catalysts is really important. So the contributions of Jamal Musayev, a computational chemist, and John Baxter, X-ray crystallographer, is really important for our understanding of how these catalysts work. So the idea is, a lot of people, of course, are thinking about selectivity in terms of CH functionalization. And by far the most established approach to do this is to do substrate-controlled CH functionalization. In other words, you have a directing group on your molecule that will coordinate to the metal and then be well placed to activate a specific CH bond. Next slide. Our concept is to make the reaction catalyst-controlled. In other words, you don't have that directing group on the molecule, and hopefully you will be able to get controlled selectivity at any of several possible CH bonds by just choosing the right catalyst. So you'll have a toolbox of catalysts to control your site selectivity. And as you can see in the compound on the right-hand side, these catalysts ideally would be able to override maybe the normal site that you'd expect CH functionalization. Probably alpha to oxygen is the most active, the hydrogen marked in blue, but with the appropriate catalyst, you could change that pattern of reactivity. So the way we approach this type of chemistry is by means of a carbene-induced CH functionalization. So the more conventional way of doing CH functionalization is shown on the bottom side in blue, where basically the metal, by some mechanism or other, inserts into the CH bond, and in that manner activates the CH bond for further functionalization. Our chemistry often will involve diazo compounds that, in the presence of a metal catalyst, will generate a highly reactive metal carbene, and that metal carbene will be what will actually do the CH functionalization. They're very reactive, and it's the carbene that actually inserts into the CH bond. So you directly now go to your final product. Now the challenge has been selectivity, because these are very reactive intermediates, and so being able to get site-selective functionalization has been a major problem. And the way to solve this has been to do the chemistry in an intramolecular sense to be able to get an appropriate reaction to occur. And indeed, on the next slide, which actually shows 1997, which is the first year that we demonstrated this idea of CH functionalization. The general opinion back then was intermolecular CH insertions, and I quote, reactions have mechanistic value but are not synthetically useful, because you really had to go to the intramolecular sense to be able to get clean, useful synthetic transformations. And indeed, at that time, virtually all of the work had been carried out on carbenes that are metal carbenes that are very reactive. These carbenes are very electron deficient, and the classic compounds that people used either had a single or two additional electron withdrawing groups, and that made them hyperelectrophilic and therefore so reactive they would be unselective in the intermolecular sense. On the next slide shows the type of carbenes that our group developed, which is what's called these donor-acceptor carbenes. In other words, you have a donor group in blue that actually will help to stabilize that really electrophilic carbene, and therefore will attenuate the reactivity. And as a consequence, unlike what was known about these carbenes, these actually are capable of doing highly enantioselective intermolecular CH functionalization. And indeed, it's nearly 20 years since we initiated this type of program with these donor acceptor carbines. Next slide, please. And what I'm doing on this particular slide is a terrible disservice to all the students that have worked in my group for the last 20 years, because I'm summarizing all of their work in this one slide. This is what happens when you have to talk in 20 minutes. And so what this is showing is that the standard chiral catalyst that we developed was this rhodium DOSP catalyst. And in terms of site selectivity, we have an interesting balance of sterics and electronics, resulting in the ultimate control of where the CH functionalization would occur. So the way these carbines behave is they actually start to abstract a hydride from the compound and then ultimately insert into the CH bond. But as a consequence, they build up positive character at the carbon that's doing the CH functionalization. And so electronically, a tertiary CH bond is going to be preferred. However, the rhodium carbene complex is sterically very demanding. And so from a steric point of view, the primary CH bond is preferred. So you have this battle between sterics and electronics. And with the standard catalyst that we've been using, this rhodium DOSP, the balance lies at a methylene site. In the work, many papers, and this was a review in 2011 that summarized all this work, we showed occasionally you could get tertiary CH functionalization if it wasn't as too sterically demanding. And you could also get primary CH insertion as long as the R group stabilized the positive charge very effectively. But in general, the chemistry went for a methylene site. Now, what we want to be able to do, next slide, is to change this normal behavior and really bring in different types of catalysts with changing the sterics. So we could go for a more bulky catalyst, a less bulky catalyst, I would go for tertiary, and then a more bulky catalyst, I would go for the primary CH bond. And on the next slide, I introduced this new catalyst that we developed, which is this triaryl cyclopropane carboxylate catalyst. Now, this catalyst was actually developed for other types of carbene chemistry, but what we found was that it behaved as it was sterically incredibly bulky. And so we thought this could open up an opportunity to take the chemistry towards the primary CH bond instead of the secondary CH bond. And next slide. And indeed, in 2014, we demonstrated this basic concept in this JACS paper, illustrating selectivity occurring at a somewhat activated site. So here is at allylic sites where you see the old catalyst, rhodium DOSP, preferentially goes for either the methylene site or the tertiary site. That's the result in the top line marked in blue, while this new catalyst did a total switchover and drove the chemistry very highly towards the primary CH bond and also achieved this reaction with very high enantioselectivity. So the second feature, next slide please, that we discovered is that if one modified the size of the ester, one could actually improve the reaction quite a bit. Now, you can't use your normal large alkyl because they will undergo intramolecular CH functionalization. So the system that works extremely well here is the trichloroethyl grouping. And you can see, if you look now at benzylic CH functionalization, the first two lines show the two catalysts going against each other. And when you use the trichloroethyl derivative, not only do you improve the site selectivity to 13:1, but you also get a reaction goes with very high enantioselectivity. And indeed, in the second JACS paper, we showed how you can think of this CH functionalization as being equivalent of an asymmetric aldol reaction when you do the CH functionalization on a methyl ether. Again, selectively going to the methyl group because of this sterically bulky catalyst. To really go for the very hard CH bonds. And of course, those are going to be the CH bonds in alkanes. In other words, we thought the combination of the trichloroethyl giving us a much more robust carbene and a more sterically demanding carbene, combined with these new catalysts, could allow us to achieve selectivity, shall we say, in a compound like pentane between C1, C2, and C3. And of course, the problem here is not just site selectivity. You've also got the possibility of enantioselectivity. And in the E2 functionalization, you've also got diastereoselectivity to worry about. So we began with our old catalyst, rhodium DOSP, expecting it to perform badly. But as you'll see in this study, we had a lot of surprises all along. Next slide, please, Dan. And what you see is that rhodium DOSP performed much better than we expected. Instead, it gave a very clean reaction towards C2, but you can see there was also a little bit of competition with C3. Now, it's pretty interesting that you can distinguish between methyl propyl and ethyl ethyl, but we thought this C3 would become a problem when we went to bigger molecules that has more internal methylenes. So we decided what we needed to do was make the competition between C1 and C2 and hopefully get none of C3. And indeed, what we found when we went to our bulky catalysts, which we thought would drive it towards C1, you can see we overcooked it because we really have driven the chemistry towards C1, but we've gone too far because we're getting a fairly poor ratio now between C1 and C2, but we're not getting any C3. Now, of course, it's pretty interesting that we could get C1 selectivity. So we decided to see if we could make the catalyst even bulkier and drive the chemistry towards C1. And on the next slide, it shows how we tried to do this, which is to put 3,5 disubstituted groupings in purple, that you can see in purple. And what happened here was a big surprise because this was expected now to go clean towards C1. And what happened, it went clean towards C2 and gave us what we really wanted was a ratio between C1 and C2 and none of the C3. So these catalysts became of great interest to us. We still needed to improve the enantioselectivity and the diastereoselectivity, but we were very excited about the regioselectivity we were getting. Is 3,5 disubstituted triaryl cyclopropane carboxylate catalyst. Next slide, please. Now, these ligands may appear rather strange to you, but actually they're very easy to make. The basic catalyst can be made in 3 steps. Basically, what you do is you do an asymmetric cyclopropanation, which will actually go with very high enantioselectivity with many of the simple aryl diazoacetates we work with. Then you have to do an ester hydrolysis, and then you followed up with a ligand exchange. However, as we were driving this process towards really bulky catalysts, we found that the cyclopropanation and enantioselectivity became variable. And with very bulky systems, it became even difficult to hydrolyze the ester. And then, of course, the ligand exchange became difficult as well. So we needed to have a plan B on how to make a library of these new catalysts. And the next slide shows how we did this. So basically what we did was we actually made this 3,5-dibromo compound using the 3-step sequence we see above. And then we followed this with an 8-step Suzuki reaction, introducing 8 aryl groups to generate the product on the already preformed catalyst. And this very quickly gave us a library of catalysts for further development. Next slide, please. And so as you can see in this picture that many of the catalysts work very well in terms of site selectivity, diastereoselectivity, and enantioselectivity. All of them go with very high yields. Next slide, Dan. But the optimum catalyst turned out to be this one with a 3,5-ditertiary butyl phenyl grouping on it. And you can see it's got high selectivity across the board. And it also has an additional advantage because of all these tertiary butyl groups, it becomes a really nice soluble catalyst for all the reactions that we're doing. Okay, next slide, please. Now, due to the time that we have, I can only show you very few examples of what we can do with this system. Next slide, please. And so one of the ideas we wanted to do was to see whether this system could actually do very difficult CH functionalizations in the presence of some functional groups. The first example is showing the reaction with octane. And of course, because our site selectivity was between C1 and C2, the ratio is actually even better in this case than what we had before. with no functionalization at the internal positions. Next slide, please. The chemistry can be carried out in the presence of halogenated alkanes, and you can see again it goes cleanly for the C2 position, and the halogens basically protects that whole chain from undergoing functionalization. Next slide, please. The silicon groups are an interesting group because we all know that you have the beta silicon effect, which means that the beta carbon to silicon stabilize positive charge buildup. But again, this is totally dominated by sterics, and the reaction goes cleanly at the C2 carbon away from the TMS group. And then finally, ester functionality is also compatible with this chemistry. We've actually demonstrated in some earlier work that esters probably react with the carbene, but that step is reversible. So ultimately, we still finish off generating CH functionalization products in these reactions as well. Okay, so the interesting question is, why do these catalysts perform so well? Next slide, please. Because as I mentioned, this catalyst was supposed to be so big, it was going to drive the chemistry towards C1. I just want to briefly mention the key design element in our catalyst. We always have a really bulky group that is so big that it does not want to exist in the periphery of the catalyst. It's really forced to either be on the top face or the bottom face of the catalyst, but it's too big to be in the periphery. And so what we have here is that this group is so big that, yes, it will be either on the top or the bottom, but if it is on the top face, then there's no room at the next carboxylate to also be on the top face. It has to be on the bottom face. So they take up what we call an up-down arrangement. And what I hopefully can show you on the next slide is a visual of what this catalyst looks like. And it's sort of, we've done a bit of, this is coming from an X-ray structure. We've done it color-coded to try and help you. And basically what you see is there are two of these 3,5 tertiary butyl phenyl groups on one face, on this top face. And there's two blue groups that you can see, and those are the phenyl group that are cis to the ester. And so what that means is that because it's up-down, it actually makes the complex adopt a D2 symmetric arrangement, so the two faces of the rhodium are the same. And also in the next slide, it's difficult to see this without having motion, and that would totally have destroyed my slides, I can assure you. What we've done here is just sort of tilt up the catalyst a little bit so that it sort of shows you that we've really got a chiral pocket around the rhodium, and that explains why this catalyst is capable of such exquisite site selectivity. We've heard the fantastic enzymic talk by David. We're sort of inspired by this. So this is a poor man's little enzyme, if you like, although maybe the rhodium's a bit more expensive. Okay, so next slide. So to finish off my talk, I want to show you, it's a great honor for me to be involved with the Center for Selective CH Functionalization. And I want to show you how being involved with this center really influences my research program. So from the material I've talked to you already, you can see that my main group focus is very much methodology development. But by being involved in this group, my program actually can be much broader. Next slide, Dan. So as I said, if I was by myself, I would just be doing carbene-induced CH functionalization or other methodology development and exploring what sort of reactions we could get out. But by being involved in the center, we can do a much deeper mechanistic understanding of this chemistry. So next slide, Dan. And this is illustrating that point. So by collaborations with people like Jamal Musayev, a computational chemist, we've been able to understand much more how the chemistry works and even develop predictive models for the enantioselectivity of these types of reactions. We're able to collaborate with John Berry to actually, was published in Science in 2013. And then we've been able to collaborate with Matt Sigman to develop predictive models to understand what are the key factors behind the site selectivity and develop predictive models so people can think about how the chemistry would work in a substrate beyond the set that we've actually explored. Next slide, please. So now with that mechanistic understanding, we can really begin to think deeper about how can we develop the catalyst design. Next slide, please. And so again, we've been able to collaborate with several groups to do this. So for example, again, with Jamal Musayev, we've been able to design a lot of interesting dirodium catalysts, including the one at the bottom right, which is another view of the catalyst I've been talking about today. We've been able to collaborate with Chris Jones, a chemical engineer at Georgia Tech, to immobilize the catalyst, because it'd be much more practical if this chemistry could be carried out in flow. And also, we've been able to collaborate with Simon Blakey. This is a program that he's driving, involving non-dirodium catalysts. So he's involved with ruthenium and iridium complexes, and has found that they have a very milder reactivity profile. So it really opens up the possibility of doing chemistry with acceptor-only carbines now, a major challenge that's been difficult, particularly in an anti-selective sense. Next slide, please. So with this mechanistic understanding and design of new catalysts, with a new catalyst, you're really set up for new methodology development. And the next slide shows the type of activities we have here. And so in this particular scheme, notice in the references on the right, the people in red are the PIs that we collaborate with, the ones in blue are the authors, the students are involved. So definitely predominantly in the methodology development, well, that's our major game. So many of these studies are carried out independently, but again, on many occasions, we also have some assistance in terms of really understanding the reaction. As I mentioned with Chris Jones, the goal here is to develop the chemistry so it can be done in a flow cell, and the pictures on the right-hand side illustrate the development of that system. Next slide, please. And so with the combination then of developing these methods, we are then in a position to really think broadly about the applications, and the next slide will illustrate how those applications are ongoing. And so we're very interested in collaborating with experts in total synthesis, for example. We've got a particular emphasis on streamlining synthesis through multiple CH functionalization. So one of our earlier forays was a collaboration with Jin Kuan Yu, which is showing us on the left-hand side, showing a rhodium and then 2 palladium catalyzed reactions carried out in sequence to get into an interesting series of compounds. More recently, on the bottom right, is a collaboration with Erik Sorensen and Jin Kuan Yu, again, using our respective CH functionalization strategies in synthesis. And then I mentioned we've also had a very interesting collaboration, as shown top left, with Professor Ken Itami's group in Japan, where, again, combining his CH functionalization strategies with ours, we were able to synthesize this compound, dictyodendrin. Another aspect we're really intrigued on is late-stage CH functionalization. And we collaborated with Novartis, Rowan Beckwith, and Larry Hammond to demonstrate that you could actually use this chemistry in compounds as elaborate as alkaloids to achieve site selectivity in those reactions. And so with that combination then, next slide, we're in a position then of a broad opportunities where we've gone from just sort of fundamental methodology development to this wide range of possibilities, from a mechanistic understanding, being able to develop really unusual types of catalysts, lots of synthetic applications, particularly in the CH functionalization field, and then these very exciting collaborations with experts in synthesis that allow us to really showcase the opportunities of this chemistry going forward. Okay, next slide, please. So this is a picture of the group taken as fairly recently. Many of these people are involved in the CH functionalization project. The person on the top left here is Quangbai Liao, as I mentioned, who's really been the driver of this alkane CH functionalization. The next slide, please. And then finally, you know, one of the things by being involved in the center, you've got a ridiculous number of collaborators to thank. And so there are many members of the center that we've really enjoyed collaborating with. And so the ones in bold are people that we've actually published with already. And the ones in italics are the ones we've got active collaborations going forward. And there's one or two we're still going to be collaborating with pretty soon as well. And also we encourage collaboration beyond the center. So there are many, many groups beyond the actual center that we also heavily engaged with as well. And also with a center like this, it's very important to recognize the administrative team, and particularly Dan Morton. He's the one who's been able to make this virtual symposia to work out. It's a lot of challenge, particularly with all the dense slides with all the pictures. They're very difficult to work in this type of setting, and it's quite remarkable what he's been able to achieve as well. And then finally, I'd like to thank you for your patience and your attention.